Hello everyone! In this mechanics, physics and statics tutorial, we explain how to find the resultant of two forces acting at a point. We will explain three approaches for solving this important problem that every engineer and scientist need to know how to solve. Let's start with a brief problem description. Two forces, F1 and F2, are acting at the point A. The intensity of the force F1 is 30 newtons and the intensity of the force F2 is 20 newtons. Our goal is to determine the resultant of the forces F1 and F2. That is, we want to find the intensity of the resultant as well as the angle of the resultant. First, we will explain a simple graphical approach for solving this problem. That is, first we will explain the so-called parallelogram method. The parallelogram method consists of 4 steps, and here's the first step. In this step, we first construct a line that's parallel to force F1. Here's the force F1, and starting from here, that is from the end of the force F2, we construct a line, given over here, that's parallel to the action line of the force F1. That is, this line is parallel to the force F1. Then, in the next step, we construct a line that's parallel to F2. Here's the force F2, and the dashed line is its action line. We construct a line starting from the end of force F1, and this line should be parallel to the force F2. And here's the line. That is, this line is parallel to the force F2. Then we determine the intersection of the two constructed lines. That is, we determine intersection of this line that's parallel to F1 and this line that's parallel to F2. And the intersection point is denoted by the point B on this graph. In step 3, we can construct our resultant. The resultant starts from A and ends at B. The resultant is actually determined by the intensity of the vector r and the angle beta. We can measure the intensity by simply using a ruler and by measuring the length of this vector. Or if you're using a CAD software, you can simply measure the length of the vector. To measure the angle beta, we can use a protractor. Or in a CAD software, you can simply measure the angle that this vector makes with the horizontal axis. And that's it. An alternative geometrical solution is to use the so-called triangle rule. Here's the main idea. In step number 1, without changing the orientation of the force F1, we simply place the beginning or the tail of the force F1 at the end or tip of the force F2. That is, we simply translate the force F1 and place it at the end of force F2. And the result will look like this. Then, in step number 2, we construct the resultant force R. The resultant force starts from the start of the force F2, that is, from the point A, and it ends at the end of F1 that's being translated. And here is the resultant force R. Then, in step number 3, we measure the length, or better to say, the intensity of the force R and the angle beta. And that's it. The third approach for solving this problem is purely numerical. The third approach is based on basic trigonometry. Namely, to be able to solve this problem, we first need to revise and review the law of cosines and the law of sines. This figure shows a general form of a triangle in the 2D plane. The corner points are A, B, and C. The lengths of the sides are A, B, and C, and the corresponding angles are alpha, beta, and gamma. The law of cosines consists of these three equations. Namely, from this figure, it follows that c squared is equal to a squared plus b squared minus 2 multiplying a, b, cosine of the angle that the sides a and b are creating. That is the cosine of the angle gamma. Similarly, we can obtain these two equations. On the other hand, this equation describes the law of sines. The law of sines tells us the following: a over sine alpha is equal to b over sine beta is equal to c over sine gamma. C over sine gamma. Now let's go back to the graph constructed by applying the triangle rule. To remind you, we constructed the force R by taking the force F1, translating that force and placing it at the end of the force F2. Then we simply connected the beginning of the force F2 to the end of the force F1, and in that way we constructed the resultant force R. The resultant force R is determined by its intensity, denoted like this, and by this angle beta. That is, we need to compute the intensity and beta. To compute the intensity of the force R, we will be using the law of cosines. Let's analyze this triangle. The angle of 15 degrees given over here and the angle of 20 degrees are given by the problem formulation. Since this angle is 20 degrees, this angle is 160 degrees. Now we are ready to apply the law of cosines. The length of this side of the triangle is simply the intensity of the force R, and I will denote it like this. The length of this side of the triangle is simply the intensity of the force F1, and the length of this side of the triangle is simply the intensity of F2. From the law of cosines, it follows: the intensity of R squared is equal to the intensity of F1 squared, that is the intensity squared of this side, plus the length of this side squared, and that's actually F2 squared, minus 2 multiplying the intensity of this side, or the length of this side, multiplying the length of this side, multiplying the cosine of the angle between F2 and F1. And this angle is 160 degrees. Next, let's simplify this equation. For that purpose, let's first construct a unit circle. The radius of this circle is equal to 1. The angle of 160 degrees can be graphically represented like this. It is the angle from here to here. This is 160 degrees, and this angle over here is actually 20 degrees. Okay, over here we have cosine of 160 degrees. Graphically, this cosine is actually the projection of this line onto the horizontal axis. That is, the cosine is equal to the length of this line with the corresponding sine. Let's see over here. This angle is 20 degrees, and we can observe from this graph that cosine of 160 degrees is actually minus cosine of 20 degrees. This is because the cosine of 20 degrees is positive. However, we can see that we are in the negative part of the horizontal axis. Consequently, we need to add a minus sign over here. This is a particular application of a standard formula in trigonometry. Namely, for any angle delta, we have that cosine of 180 minus delta is actually equal to minus cosine of delta. By substituting the derived expression in this equation, we obtain the following equation. The intensity of R squared is equal to the intensity of F1 squared plus the intensity of F2 squared plus 2 F1 intensity multiplying the intensity of F2 multiplying the cosine of 20 degrees. And finally, we obtain that the intensity of R is a square root of the right-hand side. We have intensity of F1 squared plus the intensity of F2 squared plus 2 times the intensity of F1 multiplying the intensity of F2 multiplying the cosine of 20 degrees. My suggestion to engineers and to students is to use MATLAB or Python to solve this equation, that is to compute R. And here's the Python script. First, I import NumPy as NP, then I define the forces F1 and F2, and I define the angles of 20 degrees and 15 degrees. Next, when using NumPy, cosine, and sine functions, it's very important to convert degrees to radians. And over here, I convert the two angles from degrees to radians. I simply take the angle in degrees and multiply it by 2 times pi over 360. And this will give me the angles in radians. Okay, over here, I will simply compute the resultant force. Here it is, and this is the intensity of the force. Notice that here that I'm directly implementing this equation. However, as a test, I will also implement this equation to verify my geometric and trigonometric reasoning. And here is the result. This is R computed by using the geometric and trigonometric arguments, and this is the standard formula. That is, this formula actually implements this part over here and computes R by simply taking the square root of the right-hand side. And let's test this. And you can see that R test and R are actually identical. I can simply subtract them and I will obtain 0. Okay. So the result is 27, or actually 49.270997. So let's write this value over here. The intensity of R, once you substitute all the values, is actually, let me again see, it is 49.270997. Here is the intensity of the force R once more. The next step is to compute the angle beta. To compute the angle beta, we will first need to compute the angle alpha, and then we will add 15 degrees to the computed angle alpha to obtain the angle beta. How to compute the angle alpha? Well, we need to apply the law of sines. Let's analyze again this triangle. We have computed R. Then we know F1 And we know this angle of 160 degrees. Consequently, we can write r over sine of 160 degrees is equal to, let's see from this triangle, it is equal to the intensity of F1 divided by sine alpha. Then, from this equation, it follows that sine alpha is equal to, let's see, it is the intensity of F1 divided by the intensity of R multiplying the sine of 160 degrees. From this equation, it follows that alpha is the inverse sine function, or the so-called arcsine, of the right-hand side. On the right-hand side, we have the intensity of F1 divided by the intensity of R, multiplying the sine of 160 degrees. And that's it. Let's see how to implement this formula in Python. Here it is. Over here, I will first compute alpha angle in the radians. I will do so because the arcsine function returns the angle in radians, and here I implemented the formula. This angle is 180 minus A1, and A1 is 20 degrees, and this gives 160 degrees, and over here I multiply by this part to convert everything to radians, since I need to compute the sine. And once I do that, I will simply multiply the results by 360 and divide it by 2 multiplying pi. And let's see the angle. And finally, let's see the alpha angle, and beta angle is simply alpha angle plus 15 degrees. And here it is. Let's see the beta angle. Here it is, it's 27.0197. That's it. Let's write this number over here. Beta angle is 27.0197, and the angle alpha is 12.0197. And that's it.